Yeah, thanks to all of the organizers and especially to Marisa and Jim for doing a lot of heavy lifting. Of course, everybody else who's involved, you guys made an amazing job in organizing this meeting. I really enjoy it, and it's always great to have people from many different communities interact and talk. Right. So I'll tell you about work that started shortly after this very last string data meeting. So I met Rak-Kyeong there. Many of you know Rak, and at that last string data meeting, I gave a talk pointing out that there is a problem that actually in high demand in terms of physics of understanding some structure of BPS spectra. So I'll formulate the problem in this talk, and but I won't give a motivation. So for motivation, you may want to watch the video of this last talk. And we basically started talking, and I thought that this will be a very serious, long project and so on. I'll try to explain later in the talk. But it turned out that already early on, it hasn't been such a long time really, we found an interesting signal, and it's against anything that I expected. So first, I expected that at this level of experimentation, we wouldn't find anything, machines wouldn't learn anything. And secondly, if they did learn something, I would expect completely different results. So in a way, giving it here is an opportunity for me to advertise this question, see how robust it is. Some of you may want to go and do more experiments. There is obviously more room for understanding. And if it is true, then it's actually a very interesting physics result or math result that I didn't expect. So this is a good example of conjecture generation that we're just discussing over in a coffee break. So as a result, I want to also thank organizers of the previous string data meeting for giving us the opportunity to start this collaboration and discussion. Anyway, coming back to this meeting, organizers requested that we give half-hour talks and leave about 15 minutes for questions or discussions. So I thought there is nothing wrong with starting a discussion early in the talk. So I want to ask you guys your honest opinion. So imagine, put on your physicist hat. So as many speakers pointed out, this is predominantly physics or experienced or trained audience. So imagine you're a physicist, forget anything about ML. And imagine that you're talking about conformal field theory. This is going to be the subject here. So what is the basic characteristic of a conformal field theory in your mind? OP. That's a lot of data. Something simple, simplest, something you can convey to me when we start talking. What would be the defining feature of a CFT? Yeah, that would be my answer, but I'm glad that we're generating ideas. Yeah, thank you guys. The reason I'm trying to ask this question, this is an honest question. If anybody else has other opinions, feel free to either veto or support this thought. I just want to test how much my expectation aligns with yours. Actually, I also thought that central charge is a good measure. It's just one number, and it roughly tells us how heavy is the CFT, how many degrees of freedom it has. Of course, if CFT is strongly interacting, we cannot just say it has a bunch of fields. That's a useless notion. If it's strongly interacting, there is no free field description. But central charge basically is a good approximation. And by the way, this slide is relevant to the talk, but it's completely unrelated to the question I'm asking. So the integrals have nothing to do with this question. Conformal field theory, of course, has a lot to do with this question. That's why I showed the slide. But integrals will come in later. That's right. Yes, exactly. Yes, that's another. That would be actually Jim went all the way to OP, so that's very much further down the line. Yes, I would probably say central charge spectrum of dimensions. Exactly. Yeah. Fine. Very true. So yeah, thank you for ideas, thoughts, and for helping. So also, do you know what this plot is? Continuing the interaction. Thoughts? Yeah, that's right. So I think, I don't know if it's in Gary's talk, probably to trying to ask this question as a warm-up would make sense after if we were going in reverse order. Yeah, so of course this is the CMB spectrum. So the bottom line of this talk, and I'll show you, I'll give you all the results and then kind of punchline early on. So one of the punchlines will be a plot like this, which looks kind of similar in the same way that the general picture here is profile is kind of easy, but what makes it most interesting is this acoustic peaks, this additional peaks. And here there will be same feature. So most of my focus in this talk or result will be just about this main one. And then there are this kind of smaller acoustic peaks, which actually I cannot explain. Just like in CMB, this is it's like an extra credit problem, something that I can't explain. Anyway, we'll talk about spectra, and I'll try to formulate this problem first carefully, because again, I think some of you may be actually much better at studying this problem than me. So therefore, I want to explain what I want or what community wants. And when we'll talk about spectra, again, prototypical example is, of course, harmonic oscillator. You all know the spectrum of harmonic oscillator. And it's convenient to encode the information about spectrum, namely the energy levels and how many states at a given energy level we have in this generating function. So basically, we sum over all energy levels, and we write with some formal variable q, series which has q to the energy of that level if it's present. So for instance, for harmonic oscillator, it will be just 1 power of q for every level, and of course this is just geometric series. So that's a very simple function. So later on we'll talk about various generalizations or versions of such generating series written in terms of variable q, but really what it does for us, it encodes the spectrum of states. And as indeed in this preliminary discussion we already saw, this in many physical systems, and particularly in CFT, spectrum is a good system to look at. So this is one of my favorite quotes. In fact, Sven already showed this in one of his slides as well, that all we do in physics is usually study harmonic oscillator and spectra in various much more complicated systems compared to harmonic oscillator. So this is an actual real life example of spectrum coming from one of the systems that I'll be showing you later. And this is an illustration of problem that I was asking about back at the string data a few months ago. So when we work with supersymmetric field theories, we often also count states not necessarily just with plus sign, as in harmonic oscillator. There is a natural notion of various indices, and in that case, states are counted with plus minus signs, which actually makes them more robust to analysis. So in some sense, this is a little bit more boring data because it does not capture all the richness of the dynamics, but it's also more robust and easier to compute. So we'll talk about indices which do include plus minus signs. And if we're speaking of a two-dimensional conformal field theory, or even high dimension, so this is the series. You can basically ask what about its coefficients, what data or what kind of structure it represents. And in the context of two-dimensional CFTs, there is a famous Cardy formula, which basically says that central charge, that basic characteristic of a spectrum or conformal field theory, is encoded in the behavior of its coefficients, an, when n is very large. And I encourage you to play with this or explore this structure, because spectra of many, especially two-dimensional CFTs, are reasonably well known. We can have really good grip at the problem, good understanding. But to extract this behavior, you have to go to sufficiently large n. So leaving n even a few hundred is often not enough. So you have to go typically to several thousands to actually see that. So this is just to illustrate that this basic characteristic, the central charge, or roughly number of degrees of freedom in terms of how many fields we have in a CFT, is about behavior of these coefficients or levels. So these coefficients an, they have to do with powers of q. And remember that these are basically energy. So this is behavior of the spectrum at higher energy levels, or whatever the analog of energy is. And this was indeed my initial reaction. So the problem I'm going to describe to you in the simplest possible version, which is probably the best for half-hour presentation anyway. Like I said, first I expected that we're not going to learn anything using ML. Secondly, I expected that if anything, we're probably just going to barely learn that central charge is a good characterization of CFT, because this is how I and probably many of you thought of a basic characteristic, like what's the characteristic feature. So it turned out to be not true, and the punchline is that the first gap in the spectrum is the most important feature for identifying the spectrum. And this is interesting because when I was young, roughly 20 years ago or more, I actually did study gaps with various collaborators in the spectrum. And even at present day, there are some papers and discussions involving, for example, gap conjecture and so on. And there is some feel that gap captures certain information about the spectrum, but coming into this field, even equipped with all this knowledge from the past, I would actually have never said that gap between first couple of states or first state and the second state is the best correct way to describe the spectrum. So that would be very strange. Even from the perspective of modularity, for example, or number theory, or this field has connections to many other areas of physics and mathematics, it would be really, at least to me, surprising conjecture. So that's why, again, I don't know what to make of it. If it is true, this is really interesting. It points, this gap does not really have a name. We don't really know how to characterize it both physically and mathematically. So if it is true, it's worth exploring it further, for sure. And but as you can hear, I'm presenting it with a bit of caution. I actually don't know if it's true. There is very strong signal, and that's what we're seeing, right? That's going to be the result. So the punchline is that in BPS spectra, it seems that the first gap between very low length states characterize the spectrum much better than, for example, asymptotics, which is central charge. To me, this is, again, surprising. Any questions before I proceed?
So in some cases, when you say what is most predictive, what you're actually just learning about is your training data. That your training data just has, you know, too many examples at high C, or at a given value of C. But do you think this is robust to the kind of the examples that you're looking at, or do you have some sense that you're looking at exhaustively in examples?
Yeah, so that's, I was planning to come to this much later. Yes, obviously, first thing is, actually, when we first found this, I thought this is a fluke. It will go away. Let's play with different data set. Let's explore in this another direction. And precisely for this reason, I'm inviting everybody to explore this problem further, see how robust it is. Our conclusion is that it's surprisingly robust. So again, I don't know what to make of it. Originally, I wanted this effect to go away, to be honest. I'll be completely frank, but it doesn't go away. So I don't know what to, I mean, it seems like it's an actual new physics result. And then if it is true, then we should explore it, or mathematics result. By the way, I'm mostly mathematician these days, so I haven't given a physics talk in 5 years or more. So this actually feels really good and nostalgic to talk about physics. It's been a while. Exactly. So that's right. So if it was fully modular invariant, it had a chance indeed to be related. For example, the first gap would be basically conformal dimension. So yes, it's still not central charge, but it would be very much in line of the intuition we had. So then I would accept it. But unfortunately, fortunately, systems I'm going to show you They have, Miranda is not here, I think, but we actually try to study with her this kind of systems from modular perspectives, and these are not modular at all. I mean, modular properties of this is completely unknown. So it would be interesting, I mean, if it points to some hidden modularity, oh, Miranda is back now, so then it would be interesting to uncover that. But again, it's extremely hidden. So that's this number theory perspective. If I were, I mean, just to give another perspective, for instance, if I were talking about gapped systems and condensed matter, then actually I would expect that first gap does matter, because the system is gapped and everything at high energies probably is not super relevant to crucial dynamics. So I would actually think about the first gap, but here we're talking about CFTs. So these are not gapped systems, and then this is BPS spectrum. So in that sense, to me, this is still surprising.
Hi. So
yeah.
So this gap here is like difference between the excited state's energy and ground state?
Basically, yes. Yeah. It's.
How does it matter actually? I'm still slightly confused with the notion of that.
Well, it's how it matters, that's the whole talk. So you're right. But the gap, just to be clear, that's what I was trying to explain a minute ago. The whole system is a very rich, interesting physical system. It doesn't have a gap, but we're focusing on a very special part of the spectrum called BPS states or BPS spectrum, and that looks like a spectrum of harmonic oscillator. That's why there was an analogy. And for this particular subsector of the whole theory, there is indeed a gap, and the statement is first gap matters most, second gap matters less, and so on and so forth. And that I'll quantify, explain what the problem is, and so on. Yeah.
So this gap also matters greatly in deterministic algorithms for preparing ground states of quantum field theories and quantum spin systems. So there are these
or not gap, because spin systems, if they're not conformal, I mean, we're still talking about some lattice version, right? So then of course.
So I'm talking about situations where the system looks, a physicist would call the system gapless. So you can have such situations where the first gap scales inverse polynomially with the system size, or inverse exponentially with the system size, so long as you obey some sparsity conditions of the low-lying density of state, which looks very familiar to people who study CFTs.
Right.
So I guess my question is, do you also see from this that the sparsity properties of the low-lying density of states, more so than just the first gap, is also something that matters?
It does, yeah. But yeah, so the answer is yes to this part, but I still want to emphasize contrast with systems which are either gapped or infinite volume. So this is a statement about infinite volume. In addition, I can try to put an infinite volume, and then of course, again, this expectation that lowest gap will matter and so on will be true, but it will have nothing to do with this gap in the BPS spectrum. That's a different gap, just to be clear that it's not confusing. So again, as a condensed matter physicist from way in the past, I would expect that first gap should matter, but this is not this gap. This gap is in BPS spectrum. This is something else. Again, it may be closer to modularity in some sense, but unfortunately, modular properties of these things are not known. Okay, so to tell you more about the problem, so let me define the problem and then explain where this result comes from. And again, I suspect many of you probably can do more experiments, and it would be a good idea and better experiments. So the problem that, right, so anything machine learning oriented should have potential to generate or explore large data sets. So we need data sets which are huge and easily accessible. So they should be extremely cheap and fast, okay? So here we'll focus on class of BPS spectra in three-dimensional theories which are labeled by decorated graphs. So graphs like this, they can have any number of vertices labeled by integer numbers, positive and negative. So my next job in the next couple of slides is to explain how for each of these graphs produce for you a BPS spectrum. But they come from these three-dimensional theories. So useful quantity to have is adjacency matrix of the graph. And as some of you probably already suspect that with Rak, we were planning to do some feature learning using graph neural networks, and we thought that, oh, this is perfectly made, and there is probably some rich story here. But again, in what I'm going to show you, it won't even be needed. But the problem is defined through these graphs. And in physics, especially supersymmetric field theories, graphs usually are kind of close cousins to so-called quivers, and people study quiver gauge theories, where each node in the graph represents gauge group, each edge represents some matter, and the labels of the nodes encode the rank of the gauge group. So this is not the case here. We're talking about three-dimensional gauge theories. And in 3 dimensions, you have a very special interaction called Chern-Simons interaction, or in this case, you can have supersymmetric Chern-Simons term. And the label of each vertex is actually this Chern-Simons coupling. It's not the rank. So that's very special to 3 dimensions. That's why we're focusing on 3D theories. And the reason this is in high demand or interesting physically is because we're talking about huge class of theories that could be called non-Lagrangian, meaning their weakly coupled or Lagrangian description is not known and may not even exist. Some people believe it does not even exist. So many people, mostly Hee-Jung Chung, actually devoted the whole research line trying to find Lagrangian description of these theories. And there is a lot that's known, a lot that can be said. So in some very special cases, when your entire graph consists of a single vertex, there is a Lagrangian description. But of course, that's a very poor graph. I mean, we want graphs with millions of vertices. And in general, even if we had 2 or 3, as soon as we start having edges, it seems that so far it did not lead to anything Lagrangian. So these theories are cool. There are lots of them, and we don't understand. That's the punchline. So in work with several collaborators, we try to have another perspective on these theories, and we made our own effort and attempt to understand them. So the best we could come up with is to say that these are very strange 3-dimensional theories, which are kind of like gauge theories coupled to matter, except that matter is highly nonlinear. So there is a Skyrmy type description of the matter. So what is Skyrmy? So this is Tony Skyrm. He's invented Skyrmy model originally for applications in nuclear physics as a description of quark interaction at very low energies, where we see baryons, mesons, and so on. And basically, the idea was to replace vector-valued representations of gauge groups, which is actually what we usually use when we write Lagrangians, for example, for QCD and other interactions, with group-valued fields. So this later led to chiral models and many other things, which again, in his days were called Skyrmy models. And he's actually a very interesting guy. So he lived in England most of his life. Then for some reason, he decided to go to Malaysia, and he loved the country and so on. So if, again, you don't know, I encourage you to learn more about him and his model. And here in this slide, I basically illustrate the difference between linear vector-valued matter, which is basically by definition a vector space with some group or Lie algebra acting on it, whereas group manifold is highly curved. So again, think about, say, SU2, Lie algebra versus the group. The group is basically a 3-sphere. So it is curved. And as in the previous talk, it has curvature. It's an interesting manifold and so on. Whereas Lie algebra of SU2 is just 3-dimensional vector space. It's very linear. And of course, it's approximating the group at one point, namely the identity. And both of these enjoy G action. So if we are physicists and we want to produce new types of matter, we can use actually both of them for interactions. The only difference is that in one case, it's studied for 60 years. In the second case, we have no clue. This nonlinear group-valued matter is subject that's completely unexplored. And it's hard, because it's curved, but it's interesting. And hopefully one day, once we understand landscape of QFTs way better than we do in 2023, we will be able to talk about these theories. And when that happens, I suspect that all these theories I'm talking about will have such interpretation, such a description, because it seems that ingredients that we need for these edges in the graph have to do with this matter. But again, currently, this is way outside of what we can do as physicists, as quantum field theorists. Okay, so this is why this is interesting. Now, surprisingly, even though we cannot describe the theory in full glory, we actually can describe its BPS sector, and only BPS sector, not the rest of the spectrum, precisely for the reason that it's robust, it's under better control. And this I can actually summarize for you in 2 slides. So that's fairly easy, and this is something you can code, and this is very crucial to generating a lot of data. So if you want to explore what really matters for this BPS spectra, at least from this huge sample of theories labeled by graphs, you want to be able to generate lots and lots of data. And this is how it goes. As before, we're going to encode the BPS spectrum in Q-series. And I'll tell you how, given a graph, one can produce such a Q-series. It basically has the Feynman diagram style rules, where for vertices and edges, you have basic building blocks, and then you do some overall integral. Namely, for each vertex, you introduce integration variable, which lives in a complex plane, and you integrate this huge product of basic building blocks over unit circle for each of the variables. And if your graph has, say, 100 vertices, then you have to do 100 integrals. But ingredients in this integral are very simple. And if you have a vertex, then for a variable x associated to that particular vertex, you introduce the factor written on the top. If you have an edge connecting 2 vertices, I and j, then you have variables xi, xj for each of the vertices, and you stick this factor in. You take the product over everything, and also you use theta function associated with this adjacency matrix. Remember that we introduced before. So here it looks like a mouthful, but still it's much simpler than most of Feynman integrals. In fact, this is basically a simple convolution of rational function with a theta function, and you can quickly do this by residues and convert it to big sum. So that's why it's a fast computational thing. If you're trying to code this, this is actually very fast. It's not really an integral. It's a big sum, basically. But I'm presenting it in a way how it emerged from physics, for example, of the systems. So here is another way to write it. You can package it in a slightly more compact form. The point is that if you have adjacency matrix of your graph or some data of the graph, you can very quickly compute this Q-series, which encodes for you the information about the BPS spectrum. So that's exactly what we want to know. That's exactly what we want to learn in huge class in fact, for all graphs whose vertices are labeled by integers, all kinds of integers, and that's basically the problem. At present, we don't really understand the results, so it will be some kind of Q-series. It won't be modular in general at all. It is expected that it may have some kind of hidden modular properties in a highly non-trivial way. That's why I was mentioning that you and I were, or still are, interested in this. But we don't really understand these hidden modular properties analytically, mathematically, beyond graphs, again, which have only 1 or 2 high valency vertices. So complexity of this problem is controlled by how many, say, trivalent or high valency vertices you have. And again, just 1 or 2 high valency vertices is very poor. It's clearly just beginning. So it's good to have this beginning, but it's not informing us of what happens in general at all. So again, this is a problem where even getting off the ground, either in physics or math, is extremely hard and non-trivial. So we didn't have any prediction. And that's what I kind of love in applying ML to physics or math problems, very much in the style that Magdalena described in the previous talk, is it's cool to try to do it where we don't know what the answer is, where other methods hesitate and we actually don't know. So we can actually show that ML is really useful for solving something that we could not do otherwise. So for practical purposes, in this problem, we're going to restrict ourselves to negative definite adjacency matrices. So most of the labels will be negative numbers. So this is for technical reason that is extremely interesting and so on, but I'm not going to talk about it at all. It's not really cutting space of our options by much. But anyway, this is basically the formulation. This is something you can take, code, and produce for lots of graphs, lots of data. So this is addressing one aspect of the problem, that we can have huge data set to explore, basically data set labeled by graphs. That was the question. Oh yeah, so maybe one more thing I wanted to add is that the problem to me, as I mentioned most recently, I'm interested in mathematical aspects of the story. And mathematically, this has something to do with quantum groups and very subtle invariance of three manifolds, because each such graph, as I described, namely graph whose vertices are labeled by integers, actually represents a three-dimensional manifold. So to me, this was actually a question in topology, or that's one way to think about it. So anyway, then we were hoping to do a lot of things, but we started with the most obvious thing, which is principal component analysis. So basically, you try to reduce the information about your data to a couple of basic directions in a space of your data, which encode maximal variance. And these principal components, the first, the second, and so on, could then tell you what really is going on, or what is best characterization of your, in this case, a BPS spectrum. So in particular, originally, first of all, with this PCA, like I said in the beginning, I was expecting that this is way too simple of a tool to tell us anything, and we should move on to more interesting things. And secondly, I was expecting, if anything, if you really scale our data properly and learn something, that something is likely to be telling us that, oh yes, the spectrum, either all of it or maybe the tail, contains information, because again, I was too much motivated by Cardy's result about central charge. And as a trained physicist, I was expecting that central charge is the basic characterization, but that's not the case. So anyway, that's what we basically tried to do, and we did lots of experiments. So now to address the question of robustness, there are many things you can try, many experiments you can make, and again, I encourage many of you to do it as well. Not even just using PCA, but other methods. But even with PCA, you can, for instance, extract. First, most obvious thing, you can extract this powers of Q and present this as a data point associated to a graph. Then you quickly see that as you go over different thousands or millions of graphs, your exponents, here denoted by NK or NM, they may vary quite widely. So you may want to consider various options of normalizing them and so on. You may or may not include information about degeneracies, the coefficient Cm in front of the Q powers. So again, and ask how robust is your result compared to including or not including this information. So since I already revealed the result earlier, it seems to be extremely robust to all these kinds of variations of the experiments. And I'll show you probably just one version here. So anyway, even if you start with, like I said before, the complexity of this graph is controlled by that's the only thing we know from either physics or math and prior studies, is expected to be, it's a very vague statement, by a number of vertices of high valency. So it's expected that there should be something related to that. So it's natural to start with only like few high valency vertices, 2, 3, 4, and so on. That's exactly what we were doing. And for instance, if you have the simplest possible graph, which has only 2 trivalent vertices, the total number is 6. And if you limit your numbers, which also can be chosen completely independently, in a negative range between 0 and -20, you already get 40 million graphs. So the complexity is good in a sense that it grows very fast. The data set can be humongous. And as I explained, generating the spectrum or computing the spectrum for each data point is quick. That's important for computational purposes of this. So if you choose them between, say, 0 and -15, you get 7 million. So it grows very fast. And of course, if number of vertices is higher, then it will explode extremely quickly. So then one thing we did, which is kind of a side remark, is that we did statistics on this millions of graphs, just from before we even compute the BPS spectrum, to which I'll get in a second. But it's interesting to ask how, for example, determinant of the adjacency matrix is distributed among these examples. For instance, in both low-dimensional topology, where these graphs represent 3 manifolds, or in physics, where represent physical theories, the condition of determinant equal 1, 2, 3, and some fixed number actually is a meaningful condition. That's interesting. And it turns out that out of all these millions of examples, if you mod out by obvious symmetries and impose condition that determinant equals 1, you actually cut 40 million to only 40 examples. So even that statistics was not obvious to me until we started really generating all this data. I would expect that much larger number of graphs would have determinant 1 condition, but that's something quite surprising. Anyway, this is more like curiosity. It basically shows that if you have a particular request, I want a graph with, say, determinant 1 of adjacency matrix, which again is very meaningful in that field, then it grows very slowly. Number of such graphs grows very slowly if you increase the range of your label. So it doesn't, somehow it's very logarithmic, doesn't really help. Anyway, so here is the story. So I'll actually tell you about the very, very first experiment we did. And this is what we found. So of course, the way I would present it now, I should completely remove the slide and go to most complicated tests that we did. But I want to show like the process of research and kind of a little bit of a drama that in PCA, we tried to compute the first few components, and there was clearly an outlier. So the plot literally looked like this. So there is something out of this 40 points. So for simplicity, I'll choose a sample that involves this 40. So we try to plot it, and we see that there is clearly one outlier. So okay, that's interesting. So something is going on. What the hell is going on? So of course, as in any research, you then go and zoom closer, like look at special data, like where this point is coming from, what kind of graph, is there something special about it? And yeah, this is basically labeling of all these different points with the corresponding. So what's written here on top are the integers which label the graph, and this is the data about the coefficients, or sorry, powers in the Q expansion. These are like energy levels and so on. So yeah, so we had to look at what's so special about this graph, which has integer labels 2, 3, 2, 3, 1, 1. So it doesn't look terribly special. At least compared to others, but there is actually something interesting. And this is something we should have implemented a priori, but we didn't, and it's good that machine immediately recognized this. So, but of course, we should have put this as an input. So this will be about symmetry implementation. Namely, in this problem, it's a mathematical theorem that in the computation, the simple formula that gives you for each graph the BPS spectrum, there is a symmetry that it doesn't really depend on a graph. It depends on graphs up to certain moves, very few moves that you're allowed to make. And in this case, the moves are such that if you see plus minus ones, you can remove them with a certain rule. So there is a certain equivalence relation that allows you to change one graph to another graph. So this is an interesting instance, which is relevant to many problems in low-dimensional topology, in combinatorial group theory, and many other topics. Again, to me, most familiar from various fields of math, where you have a symmetry, and this is in the language of talks from yesterday, it's an exact symmetry. It's not approximate. It's a full equivalence. We can easily describe how it's generated, but it's not presented to us as a group. And in terms of representation theory, we would be talking about infinite dimensional representations here, because the number of such graphs, even in each equivalence class, is infinite and so on. So I don't know how to encode this kind of equivariance or this kind of symmetry. So if we develop techniques that would be extremely useful, because many other projects that we did with Fabian and Jim are exactly of this type. So we're basically trying to learn equivalence classes or conjugacy classes with respect to this exact symmetry, but it's not the usual symmetry in a sense of finite group, not at all. But it is very group-like symmetry, and it's very easily described. I mean, these are just sets of moves. Anyway, so what happens here is that with this well-known moves, and again, this is a theorem that what I gave you is invariant under such moves. The point is, if you see plus minus ones, for example, on edges which terminate, I don't think I can point with a laser pointer, but I'm pointing at the upper right diagram, then you can remove this vertices at the cost of changing the other labels by plus minus one accordingly. And what happens with the graph that with this particular outlier, so this is again the outlier, the guy we had to look at carefully, is that you first of all see that there are lots of plus minus ones in various other places. So yes, these are vertices that you can remove, so you can actually simplify the graph somewhat. But this one is very special. It's very special in a way that as soon as you remove plus minus ones here, the other vertices change in such a way that they also become plus minus one. And then you can actually continue the process. So this is the only graph that is on this list that you can minimize to just one single point, one single vertex. And for that, everything trivializes. So again, we didn't put this as an input. Perhaps we should have, and now we did. But first of all, this was learned quickly and independently. And it's good that we didn't for the following reasons. So first, it's a good sanity check, and now we know how things work. But secondly, in this data set, and in many other versions that we explored, we didn't really at first discriminate between graphs that have, say, 2, 3, or 1, or 5 trivalent vertices. And this points to the fact that when everything trivializes all the way, yes, the answer changes qualitatively. That's the outlier. And that's actually something we did expect, because in that case, BPS spectrum is completely trivial. There is no even Q series. That's it. It's basically just one term. But in every other case, it actually, what the mistake that we made along the way shows that it doesn't really matter whether we have 2, 3, 4 trivalent vertices or high valency vertices. So this stratification of the data set by number of high valency vertices does not seem to change the result too much. And that's basically one other outcome that that came from this. So yeah, then this is how a general representative of this BPS spectrum or Q series looks like. It starts with some leading power, which we can factor out. Then there is a constant term and next term and so on. And in terms of principal component analysis, this is what correlations look like. So there is obviously very first strong peak, which points at the first gap. So that's the result I announced before. And then again, you can try to do experiments by playing with the data set. So I already mentioned this briefly. You can also experiment with different ways of truncating your Q series at either certain value, or a better idea is actually to include or not include certain number of terms, because there is a huge variance in terms of how powers are distributed. So they can vary. The first gap can be only 10, as in this example. It can be 100. It can be just 1, 2, 3, or something like that. So it's good to normalize things. And if you do that and keep fixed number of terms, you can ask, okay, how does my data change if I keep, for example, 20 or 25 or 30 terms? And one thing that persists is clearly peak in the beginning. And then if you increase the number of terms that you include, then you do see this acoustic peaks, which I mentioned earlier, but they're kind of small. And as ripples, they just get pushed away further and further into smaller values. So that, again, I don't know how to explain. I didn't even try because I did try to explain this main peak, the gap, and even that I don't know how to explain. So that's again the punchline. So it seems to be surprisingly robust to all kinds of experiments. It's extremely simple result that, again, I didn't expect to find at this stage at all. And I'm curious to what extent it survives further test checks. And if it is really correct signal, then we should have a nice physics explanation. I'm more of a mathematician, so I care about math explanation. But either way, it would be nice to explain if this is really there. Yeah. Right, so these are, in PCA, this is correlation with respect to, so these are, right, so this is length of the data set, and we are basically slicing. So this data can be presented in many different ways. So the one I'm showing here is one of the simplest, where we take a Q series or BPS spectrum, we throw away the coefficients. We don't even look at the coefficients of the Q terms. Then we take powers. I think I denoted them by NK in previous slides. And with some normalized version where you take NK divided by N1, you basically feed this vector of data as the data point for each graph, right? So, and then this PCA basically is trying to tell which of these components is strongest, is most meaningful. And it's the first one. So that's basically the first gap. So depending on normalization, of course, if I normalize by N1, automatically N2 becomes the strongest. And then I believe that's what's shown here. So it's like the second gap. But still, it confirms the surprising idea. If we don't do normalization, it will be N1. It confirms the idea that the first gaps matter a lot. And I don't know, if Kumran was in the audience, he has the gap conjectures and many other things. I'm sure he would be very happy and probably would say that this was expected for some reasons, which again, I think should be explored. To me, this was not obviously known and not even expected. Even up to present day, I don't have a really good explanation why this happened. Physical or mathematical.
So in a sense, in your case, the way you construct the features, the first principal component is just the first feature.
Yeah.
And the explained variance of that is 90. Can I read this off from this graph?
Well, it's properly normalized, but yeah, so here it goes up to 0.8 and so on. Yeah. What I didn't expect is, I mean, I was expecting that as we do experiments, check it against robustness and in various regimes and from various ways of preparing data set, that it would go away or get distributed or shifted in a lower part of the spectrum, but it didn't happen at all. And that's surprising.
I again just want to make sure I understand the data. So fix a 3D n equals 2 theory and the associated graph, compute the Q series, and then take the exponents and put it in a vector and normalize it,
Yep.
and then do PCA on that.
Yep, exactly.
And
well, then we did all other kinds of things, including, not including the coefficients. It doesn't change anything, qualitatively at least.
yeah, and maybe I'm curious if you agree with this. Sometimes in applying things in theory, in sort of formal theory and in math, even simple things like PCA can uncover things that are unexpected. Okay. Are you going to comment on where you guys might go from here? I mean, are you going to?
No, I mean, that's basically it. So you just said it. So I want to know if this is indeed an example where, like, conjecture generation, where this is a result that is true and should be proven to me mathematically as a theorem or physically with a very nice, clear physical explanation, or it's still for some reason is not general and will go away if we do something. But then I don't know what the something is, because at this point we explored all kinds of graphs, data sets. So at least for this class of problems, it seems robust. But I wanted somebody to find regime where it breaks.
So can I ask one more question? I mean, you're making the point that you thought that the answer would have been the central charge.
Yes.
And you're seeing here that there's this particular first gap that really matters. I think the thing that I'm missing is in this data, where is the central charge? Because in somehow you're saying that it's more important than the central charge, but I don't see where the central charge
Right.
appears.
So with Miranda and other collaborators, we also focused on that aspect of studying central charge. That by itself is extremely interesting quantity and so on and so forth. But it would be basically highlighting the rest of the spectrum. So what I was trying to explain in the beginning, it would be shifting this graph such that center of mass of this graph would be somewhere here.
That's a Carty growth.
Exactly.
Okay.
I don't know what the curve would be. It could be either universal that all values matter equally, or it could be heavily skewed toward the end of distribution. But again, this is exactly opposite distribution to what I'm seeing here. So this is not the central charge. It's yeah. So anyway, I don't know what to make of it. I'm completely honest, and it's a surprising, interesting result. I don't know if it's correct. I mean, it's correct in terms of experimentation, but theoretically, is there proof? That I don't know. All right, so this is it. I said everything I could have said, and the last slide is basically advertisement. So we will be organizing 2 meetings back to back, and hopefully this will be very fruitful and useful interaction between math, NML, and string data. So for example, Jim is heavily involved in organizing string data at Caltech. It will happen in December. So these are websites, dates. Please mark your calendar, and many things are still under construction, including the websites, but I really look forward to welcoming all of you to Pasadena. Thank you.
Thank you very much, Sergei.
So you said very early on that the first gap matters the most. Is it that do you mean that the first gap matters the most in characterizing a theory?
Well, in a very specific sense of PCA, for example, that it lights up higher than the second gap and so on. Yeah.
And you checked it for a lot of like the data was all the graphs with like 2 vertices and just 1 edge.
Well, we went, yeah, so that was among the early experiments. So we checked it for, we're actually most interested in graphs which have higher number of high valency vertices. So 3, 4, 5, and so on. We didn't go much higher. What's interesting, we try to ask, does it vary, for example, if we mix and match, which is how it happened historically. We didn't even pay attention to these Kirby moves and included all graphs that could be even simplified by Kirby moves to something smaller. So then just for clarity of the experiment, we decided, okay, let's separate the data and go kind of check it more carefully. What is reducible to simpler ones versus the ones which actually don't reduce. So in other words, could the answer in language of high depth modularity that is expected, could it depend on depth? And the answer is it doesn't. So it seems like it's very robust to this dimension as well. So, but again, I want somebody to do more experiments and study it further, because there is clearly a lot of interesting data in here.
Okay, in the interest of time, we take last question by Miranda.
So doesn't it mean that the central charge structure, the fact that, there is a central charge structure is kind of universal?
A central charge structure is what?
Universal. Universal among these.
Oh, no, no. Yeah, so that could be another interesting actually, my initial reaction is no, but let's discuss it further. I don't think so. So among this theories, central charge also varies wildly, and I think to me it's messages that expectation about central charge was probably off. But again, since we can discuss in much more technical level.
Central charge is universal, but the structure that there is a central charge like growth. It's probably characterizing. But let's talk.
Yeah, so one that's where the answer was no. It's definitely central charge is not characterizing the spectrum. So that's I'm pretty sure, at least in huge data sets. Well, right, but here the question is which single number, what feature in the sense of feature learning characterizes the spectrum most? Yeah, and it's definitely not the central charge. So that's for sure.
Like behavior.
Okay, let's.
I think that's a great question. So yeah, let's discuss it.
All right, that's thanks, Sergei, again.